In this section, we're going to start linking the lines that you see, the atomic lines that you see for atoms to where those electrons are. And it's called the Bohr theory of the hydrogen atom, because in reality it only works for hydrogen. It doesn't work for any other atom, but it was a good theory to start with. So Niels Bohr, another German physicist, developed a new atomic theory in 1913. And to understand this, we first need to understand that there are two types of spectrum out there. There's the continuous spectrum, which is all wavelengths of light. This is Roy G. Biv. Okay, so red, orange, yellow, green, blue, indigo, violet. Okay, and then you have a line spectrum, which only contains certain colors. And this is a line spectrum here, or it's also called an emission spectrum because this is from an element, which we'll see in just a second. So Bohr's postulates took two things. First, from Planck, he took the fact that electrons have only specific energy values in the atom. That's what we just did. And that the transition can only be between distinct levels inside of the atom. And so here are some emission spectrums of some elements: cadmium, barium, mercury, thallium. Thallium only has the one. Cadmium has, well, there's two down here, so 7 of them. Okay, barium has quite a few. All right. And from this, they developed what's called the Rydberg equation when you put these two postulates together. So the Rydberg equation links the energy to the levels in the electron. So, and because we know we can relate energy to wavelength, it rearranged to be this. 1 over the wavelength, or 1 over lambda, is R sub h, another constant, 2.18 times 10 to the minus 18 joules. H is still Planck's constant. C is the speed of light. So this is where we manipulate the energy to get the wavelength. Okay, is 1 over the final electron level squared minus 1 over the initial electron level. So F is for final, I is for initial. It's not the first time we've seen that. This one's final. This one is initial. Okay. Now this is the equation given, but this is a constant. These 3 things right here are constant. So if I take 2.18 times 10 to the minus 18th divided by 6.63 times 10 to the minus 34th and divide by 3.0 times 10 to the 8th, then I get basically R, and R is 1.097 times 10 to the 7th. So I don't give you this equation, but a lot of times you will see this if you go look at other sources for how to do this information. They'll start with this R value instead, okay, which is just because these 3 values here are a constant. But I do give you this equation if I give you a formula sheet, okay? And this will be the equation that I will be using, okay? So the first problem says, what is the wavelength? So wavelength is lambda. When an electron goes from 3, so that's initial because it's from, to n is equal, so therefore it's going to, so that's final, 2. Okay, and so the equation is that 1 over lambda is R sub h over hc times 1 over n final squared minus 1 over initial squared. Okay, so 1 over lambda is 2.18 times 10 to the negative 18 divided by 6.63 times 10 to the minus 34. The other advantage of doing it this way is I give you all these constants. I do not give you the 1.097 times 10 to the 7th. So that's the other advantage to learning how to do it this way. 3.0 times 10 to the 8th. Whoops. Is 1 over the final then is 2. So it's 2 squared minus 1 over the initial, which is 3 squared. So it is a fact, though, that when I enter these 3 things into the calculator, I get 1.097 times 10 to the 7th. 1 over 2 squared is 1 over 4, minus 1 over 3 squared is 1 over 9. So I get 1 divided by lambda is 1.097 times 10 to the 7th. And when I subtract 0.25 minus 1/9, I get 0.139. 1.389, sorry. I multiply these two terms together, so 1 over lambda, and I get 1523,611.1. Okay, but this is 1 over lambda. So if I take 1 divided by lambda, I get lambda. And I can enter this as being 1 divided by this 1523,611.1. Or I can say 1523,611.1 to the negative 1. Either way, I get lambda as being 656.3. Oops. 656.3 times 10 to the minus 7th meters. And just for the record, this was actually the wavelength that we used a couple of videos ago as the hydrogen emission line. Okay. All right, we're going to pause here, and I'm going to come back with the next video with one more problem.